Hello and welcome to lesson 2.1, estimating with finite sums. So today what we're going to do is we're actually going to calculate the area underneath a function and see why that is helpful. So let's start with an example just to understand this a little bit better. So let's say an object is moving at 10 meters per second for 20 seconds. So what we're going to do is we're going to use this graph that you see right here of this red function. And this red function represents speed. So this is, the velocity is 10 meters per second. And it's constant going through this. Now you can see I've only got this domain up to the value of 20. So in order to find this, we remember that distance is equal to speed times time. So up to 20 seconds, because this is just 20 seconds right here. To calculate this, all we do is we're just taking this calculation of speed times time. Well, the speed is 10, time is 20, which is 200. And if you remember from grade school, when you learned about multiplication, multiplication is just the area between two sets of values. It's the area between two values. One value right here being 20 and one value being 10. This gives you the area. And therefore the total distance traveled turns out to be 200 meters. Well, one other thing you notice is this value, this unit, is in meters, not in meters per second, not in seconds. It's in meters. So, now what if the shape T turned out to be varied over time? What if it didn't turn out to be linear, just horizontally linear like this one? What if it's a regular shape like this blue curve that I have right here? Well, the best option that we could probably do is we can create little rectangles underneath the function. I'm just creating a bunch of rectangles right here underneath this function. And this is the best kind of approximation I can get. I can work out the area for this piece, and this piece, and this piece, and this piece, and add them up. Well, what you're going to notice is some parts of this function are missing pieces, which I'm showing you in red right now. These areas I'm missing in red. But I also have areas that I'm counting over more. So these areas that I'm drawing in green. So it's not 100% accurate, but it gives us a pretty good estimate of what the area would be underneath the function. Now what we do is we call these areas, these actually just the lengths that we're looking at, these are called subintervals. And you can choose a size of any subinterval you want. You can choose a subinterval, in this case, most of them are 3, the last one is 2, but you can choose lengths of 1, you can choose lengths of 0.5, you can choose whatever length or subinterval you wish. So let's see the various different methods, and one of the methods I used right here. So, what we're going to do is we're going to suppose the velocity of an object is given by this function v of t equals t squared. T squared is a pretty easy calculation or function that we can use, and what we wish to do is find the total distance traveled within the first 3 seconds. So I'm going to show you different methods that are covered with these types of functions. So let's say our first instance, we use what are called 3 subintervals of length 1 using the left rectangular approximation method, also called LRAM for short. What it does is it takes the left-handmost part of each subinterval, and if we're using 3 subintervals of 1, so that means I got to start at 0, and I got to go to 1, then 1 to 2, and then 2 to 3. This will create 3 subintervals. For the left-hand rectangular approximation method, we take the left-hand point and we create a rectangle of it. So the first rectangle, you can see, just based on this horizontal black line, doesn't have a height of anything. For the next one, we'll have this height, and the next one would have this height. So using this LRAM method, I'll put LRAM. Often you put a subscript 3 to find the area of that. The area of the first one has a length of 1, but a height of 0. The next one has a length of 1 and has a height of 1. And the last one has a length of 1 and a height of 4. You notice these values right here. This turns out to be 0 squared. This one turns out to be 1 squared. This one turns out to be 2 squared. So this LRAM turns out to be 5. And there we can see that this is approximately 5. And if this was in seconds, this based on this velocity, this would be 5 units. 5 meters, let's say. Well, LRAM, as you can see, we're missing a lot of space. Missing all this area that I'm drawing in red right here. So, with this kind of function, not a very good option. We're missing a lot. So, let's try right rectangular approximation method. Similar idea, just this time, we're using the right-hand points of each of our subintervals. And then we're creating rectangles based on those values. So the rectangles have that height. So here I'm drawing the rectangles. So the RAM have a subinterval 3. Again, length is 1. This time the height is 1. Length is 1. Height is 4. And length is 1 and height is 9. So in this case, this turns out to be 14. But in this case, again, you see you have more area being covered, which I'm drawing in green right here. So this, as you can see, is an overestimation, and the previous one was an underestimation. So many people think, oh, well, if we're not going to do the left, if we're not going to do the right, let's take a midpoint within our subintervals. So let's see how that one works. This one you might need a calculator to figure out some of the values, but I'll show you it's not so bad. Okay? So again, what we do is we have our subintervals of 3 subintervals, 1, 2, and 3, but the middle point of 1 from 0 is 0.5. The middle point of between 1 and 2 is 1.5. And the middle point of 2 and 3 is 2.5. So what we're going to do is we're going to actually create points on our function at each of these values. And we're going to create our rectangles from that. Okay, so with the MRAM of 3, well, this first one, 1, times, now the height is given by, again, 0.5 squared, based on the function. The next one is 1 times 1.5 squared. And the last one is 1 times 2.5 squared. So we're going to calculate each one of these areas. Well, 0.5 squared is just 0.25. 1.5 squared is just, let's see, using my calculator for a second. That's 2.25. And 2.5 squared is 6.25. Adding these values together, I get a value of 8.75. So that 5 doesn't look good. We'll fix that. So you can see this area turns out to be probably the best option that we can have here in order to find this this area underneath this curve, because it has pieces that are both above and below. So it kind of like averages out the two. But again, you can still see this might be slightly off or slightly under. So we're going to find other methods to find this out a little later, but it's not too difficult to see. The more we subdivide the intervals into smaller rectangles, the more accurate the area underneath the curve would be. So you can probably see where we're going with this, but we'll leave that at the moment. Okay, so we're going to take this idea and go a little further and see if we can use this to estimate the volume of a sphere with a radius of 3. Now, as you can see to the far right, my drawing for my function is a graph of a circle. A circle is not a sphere. But what we can do is we can use some ideas here, because what we can do is we can take a, I'm going to draw this right here for a second. We can take a little piece, rotate it around our x-axis. Sorry, drew that wrong. To take a cylinder and rotate it around the x-axis. And this will just give the subinterval right here of 1 to give you just the volume of the sphere. A sphere, if you actually rotate this circle around the x-axis like this, you'll get a sphere as a shape. Now we know the volume of a cylinder. The volume of a cylinder is given by pi r squared h, the value we know. I'm going to use the subintervals of 0 to 1, 1 to 2, and 2 to 3 to help me work this value out. So the midpoint on 0 to 1 is 0.5, the midpoint on 1 to 2 is 1.5, and the midpoint of 2 to 3, 2.5. Now, this is our radius, and this part is the height of each of these cylinders. So to figure out the radius, we'll notice that radius squared is just whatever the y value is squared. And the y value in this expression, based on this circle is just 9 minus x squared equals y squared. Or, if you wish, x squared plus y squared equals 9. That's the equation of a circle. We know that. So to find out this value of y squared, all we have to do is just take 9 minus whatever x squared is. So our x value here is 0.5. I'm going to grab my calculator here. I'm going to do 9 minus 0.5 squared. And that's 8.75. Next I'm going to do 9 minus 1.5 squared. That's 6.75. And last but not least, 9 minus 2.5 squared. That's 2.75. Now each of the heights is our change in x values, which is just 1. So now I'm going to have to multiply these values plus times the value of pi, so I get 8.75 pi, 6.75 pi, and 2.75 pi. So a good approximation of this volume is just 8.75 pi plus 6.75 pi plus 2.75 pi. I'm going to take this 8.75 and 6.75 plus 2.75, and I get 18.25 pi, approximately. So I'm going to say the volume of the sphere is approximately 18.25 pi. Let's actually compare this to the actual volume of a sphere. You know the volume of a sphere formula. It's 4/3 pi r cubed. In this case, r is the value 3. So 4/3 pi, 3 squared, 3 cubed. If I can cancel out 1, 3 with 1, 3, make that a 2. So 3 times 3 is 9, 9 times 4 is 36. 36 pi. Oh, but remember that this value right here, oops, I forgot something. This actual volume I have to multiply by 2. So 18.25 times 2 is 36.5 pi. That's why these values are just slightly different. But they're very close to being the same volume. And there we can see this works for various different areas, just using an approximation. Thus concludes this lesson.